Air up here. Free surface. The gate popped up here. Water pressure acting on the bottom, pushing it this way. Weight of the gate acting to the centroid. Wants to pull it down this way. We were supposed to see if the gate was in equilibrium at that position or would it drop. So I'm going to just fill in some things that's already in your notes so you can add to it. We found before that FR, the resultant force, is 104.1 in your notes. And now we're looking at where that force acts. I think I might have had an incorrect symbol on here. The Y sub C, the distance down to the centroid. Okay, the centroid of the gate right here, the weight acts vertically down from the centroid. If the top to the bottom of the gate is 3 meters, the distance down to the centroid, 1.5, 45-degree angle. Y sub C measured along the inclined direction. H is measured vertically up and down. Y along the inclined surface. From the free surface to that point, the right-hand side, the 45-degree triangle, 1.5 plus 1. Hypotenuse square root 2. So 1 plus 1.5 square root 2. Okay, that's Y sub C. The distance from the free surface measured along the inclined axis to the centroid of the surface you're looking at. Okay, let's see what else we have. Oh, I sub xc. I sub xc. In the textbook, 1/12 b h cubed the base. Here's the surface. Here's the incline. Look at this. What's the base? This. What's the height? Don't get the H's confused. Okay, sorry about that. That's the height of the rectangle. This is the base of the rectangle. So here's the base. Here's the height. Here it is sitting here. Here's the base. How deep into the paper? 1. What's the height? This, which is this distance right here. It's this distance right here. Okay, so get the B and the H correct. Okay, base is 1. Height, 3 meters. Hypotenuse, 3 square root 2. Quantity cubed. I sub xc. I don't think we put all the more details in that last time, but I want to make sure that you see how we did that. 6.36. This is in meters to the fourth. I'll put the area down there. Area, base times height. The base is 1. The height, 3 square root 2. So the area, I left it like that. So put that in for here. Y sub R is Y sub C, 3.54. Plus Ix about the centroidal axis, 6.36. That's the numerator, divided by y sub c, 3.54, divided by a, 3 square root 2, y sub r, 3.96 meters. Measured from where? From the free surface down to the location of the surface where the resultant force acts. Okay, I'll show the gate again. Okay. There's the water surface up here. Here's the gate. Hinge point. F sub r acting here. The distance down from here to here. Okay, here's the incline, where the incline meets the top surface, right there. So the distance from my finger to my finger is y sub r, 3.96. The distance from here to here (3 + 1, 4). There's a big triangle here. Okay, 4 top to bottom. Hypotenuse 4 square root 2. What we want to know, if we sum moments about point O, the hinge point. I'll call it point 0. No, that's right here. I'm interested in how far from the hinge point to FR, that distance. Well, you can see what it is. So that distance, you can call it D if you want. D equal the total distance, 4 square root 2, minus this distance, 3.96, is 1.70 meters. So that's how we find the moment arm to sum moments. I left out a lot of details, and I probably better go through it to make sure you really see what's going on and not just put the numbers on there and let you try it yourself. Yeah, it takes a little thought. And what really helps? Oh, what really helps is drawing pictures. You try and do that without drawing pictures, well, you know, good luck. Especially under the pressure of a 75-minute exam, when your mind goes blank sometimes. So, of course, the lesson is, the more pictures you draw, the clearer things become to you. That's pretty much a general rule. Free body diagram and statics. Why? You know, those open up a lot of eyes. Okay, so got that straightened out. The next topic. All right, we take something like that picture over there, but a little bit different. There's no gate now. Another example. All right, so here's the top free surface. I think I'm just going to draw these as lines. Okay, this is out of scale pretty dramatically, that's okay. This is 10 feet. This is 5 feet. This is oil. This is water. This is point A. This is B. This is C. This angle is 45 degrees. Okay, this reservoir is 1 unit deep into the ground. So it's, let's call it the width. The width is 1 meter into the blackboard. So we can get an area that way. Let's see where it has to find F sub R. Okay. This is a case where we have 2 fluids. Yeah.
Are we using both feet and meters?
Oh, yeah. Thanks. We shifted gears into 2 problems. This is our English problem. Thank you. Okay, now let's go see what we got here. Okay, get FR. I'm going to first of all show you a pressure diagram. So I'm going to go down this fluid from the top to the bottom here. Okay, at the top the pressure is 0 gauge. Okay. As we go down in the oil, the pressure gets bigger linearly. Okay. So it looks, let's see what that is. There's the pressure due to oil. Pressure at A. This is the pressure at B. Now we go down in the water. Well, water is heavier. Gamma is bigger for water. So if you go down in water, the pressure gets bigger, faster than it does in oil. That's how the pressure looks through the water layer. They're both linear, but they have different slopes because their gammas are different. Remember that dP dz equal gamma minus sign, that's okay. So, gamma is a slope of that pressure diagram. Oil, gamma is small slope. Water, gamma is big slope. So that's how you tell how it looks. Now we can't do this problem like we did that problem, because if you want to plot the pressure over here from the top up here to where the gate is, the pressure looks like this. Yeah, it's just one triangle. So there are a couple ways to solve this problem. One is to treat this as a distributed load and just go ahead and find it from methods like you did in statics, similar to statics. Or what we're going to do, if you're asked for the force, put this down, write this down, on BC. If you're asked for the resultant force on BC, get rid of the oil and replace the oil with an equivalent layer of water. Okay. A to B, B to C, over here. Okay. Now we've got, this was, I'm going to make this more to scale. Notice that they both have the same pressure at point B. The pressure in the oil and the pressure in the water at point B are the same. You know, of course, you expect that. So, gamma is 8/10. 8/10 times as heavy. 8/10 times 4 feet, 5 feet. 8/10 times 5 feet. 4 feet, 4 feet. Replace the oil with a layer of water 4 feet high. Here's 10, here's 4. Now it's all water. Why is that 4 feet again? Okay. The pressure at B equal 5 feet of oil times gamma oil. Okay. That's also equal to how thick a layer of water, we call that H of water, times gamma of water. Okay. I don't know this guy. Solve for him. Depth of the water to replace the oil. Water is 5 gamma of oil over gamma of water equal 5 times specific gravity of oil. 0.8. 5 times 0.8. How many feet? 4 feet. That's how you know how much water to replace the oil with. Okay, once you convert all to water, now life is easy. Now it looks something like that guy over there. A submerged inclined surface, 4 feet down from the top. You would work it the same way that you worked that one over there, if you want to work it up. The answer is F sub R on BC is 562 times the area. I didn't get the area, but you can get the area. The area is 10 square root 2 times 1. So that's a good way to handle layers of different fluids. Try and change it so you have only one fluid to work with, and then work them like you did the previous examples. Okay, now that takes care of that one. All right. So I'm going to compare. We talked about the pressure prism last time. And we said you can use that if you wish for some simpler problems. Simpler problems are submerged rectangular surfaces especially. Okay, so I'm going to work this problem side by side, 2 different ways. We've done it one way already, so I'll do it again. Free surface. Gamma water. Okay, 45 degrees. Ten feet, 4 feet. A, B, C. We'll work it the way we previously worked it. F resultant on the surface BC. We're looking at the force on one side, so we're looking at the force on the bottom, okay, due to the water over here. All right, it was similar to the last problem. The force on the water on surface BC down here pushing up, okay. It's gamma H sub C times A. Gamma 62.4 pounds per cubic foot. H sub C, the vertical distance down from the free surface to the centroid of the surface of interest. Free surface. Centroid, 4 plus 5, 9. That's where it came from. Area of the inclined surface, 10 square root 2, assume it's 1. 10 square root 2 times 1. Okay. F sub R, 79.42 pounds. Okay. Next step, as we know, find out where it acts. Y sub R. Okay, I just found our y sub c is the incline. The incline is 9 square root 2. Okay, where's the centroid? Right here. How far vertically down? 4 plus 5, 9. Okay, so 9 top to centroid, 5 and 4 is 9. The incline distance? 9 square root 2 plus 9 square root 2 area 10 square root 2 times 1 I 1/12 base 1 height 10 square root 2 cubed 112 pH cubed rectangle 14.04 feet. From the free surface, measure down the incline. Okay, that's the way we've been doing it. Now, we can also do it another way. Okay, let's see. Did I say 1404? I mean 1404. I didn't mean 1404. Oh yeah, okay. Same picture. I'm going to redraw it though. Okay, 45 degrees, 10 to 4. ABC. We're looking at the force on one side of this, the lower side of this, caused by the water. 4, 10. Okay. I'm going to draw one more over here and then come back to that just a minute. This might help you to see this. Somewhat new problem, but it's very similar. Meters. Now let's just, I'm sorry, let's make this 2 meters. Not that way, 2 meters this way. We'll make life easy, 45 degrees. Gamma water. Air down here, air up here. We talked about the pressure prism, and I'll remind you we had a pressure prism. It's a pressure diagram, and you show the pressure acting on the surface as you go down deeper into the water. The pressure goes up. The pressure prism looks something like this. The highest pressure at the deepest point. Pressure prism. And we mentioned how you would tackle that. If you recall, we had the pressure down here. Let me mark this down here. The pressure right there, at this point right here, that pressure line. How far down are you from the free surface? 2 meters down. Okay, what's the pressure there? 2 times gamma of water. Okay, we said the resultant force is the area under that little pressure prism, which is a triangle in this case. So the resultant force is equal to 1/2 base times height. Okay, 1/2 base times height. Base. Okay, here's the base right here. 2 square root 2. I'm sorry, the base. That's the height. What is the? There it is. What's the height from here to here? Height here to here. 2 square root 2. What's the base? And I'll take it 1 again. These are all 1 into the blackboard. Okay. I think that's all I need on that one. All right, that's F sub r. I didn't number crunch, I don't think. No, I didn't number crunch. Gamma. Oh. Base. This is the height, pardon me. Get my base and height right. We're not doing the calculation over there for the area of moment of inertia. Here's a triangle. What's the base? Okay. The base and the height, 2 gamma water. That's the height. What's the base? 2 square root 2. Loading diagram in vector statics. How do you find the equivalent load? Take the area under the triangle. What's the area under the triangle? 1/2 base times height. What's the base? Here. What's the height? Here. That's how you find resultant force, statics. Over here, pressure prism. Turn it to be a triangle. How do you find the area, which happens to be the resultant force? You take the base, remember the base here to here. The base here to here, there. The height is the value over here of kilonewtons per meter right here. The height over here at the end, 2 gamma W on 2 square root 2 gamma water. Okay. Over here, statics. When you replace this with an equivalent force, this is for statics. When you replace this with an equivalent force, Fr, where do you put it? If you recall, the answer is you put it acting vertically through the centroid of that loading diagram. One-third, 2/3, pardon me, 2/3 L, 1/3 L. Well, guess where this one goes through? Well, I'll tell you. The same spot. 2/3 the way down from my fingertip. 2/3 the way down from my fingertip. So the resultant force here, F sub R, would act, let me get that guy out of there, would act at 2/3. What is that distance? We have it right here, 2 square root 2. 2/3 of 2 square root 2. Okay. Now, if you want to do this the old way, you can also do that the old way. Let's see, what would F sub R be? F sub R, let's go over here. Gamma H sub C times A. Gamma H sub C times A. Gamma H sub C, the distance down from here down to the centroid. Where's the centroid? Halfway down. That's 2 meters. Halfway down, 1 meter. It's the area of that plate. 1 into the blackboard. Hypotenuse, 2 square root 2. Of course you get the same answer, you better. But you've got a choice of sorts. If you want to always use the equations, because they're always right. If you want to always use the equations, here they are. Here's the equation for F sub R. Here's the equation for Y sub R. They're always right for a plane surface. Can the surface be triangular? Yes. Can the surface be circular? Yes. Semicircular? Yes. Quarter circular? Yes. This method right here, oh, you got to be really, really careful. It's only good for what we did here with this showing right here. That's only for rectangles. Triangles, no. Circles, no. Is it maybe easier to do like you did back in statics? Maybe. But you've got to watch out where you use it, because you can misuse it just as easily. And you, by the way, you can also find where it acts. You'll get 2/3 of that track yourself by this equation up here. Okay, you get the same answer for y sub r2. I'm not going to go through that though. So, you know, my point is, they mention this in the textbook. You might hear this in some other courses you take, in hydraulics, for instance. That's the pressure prism. It works especially well for rectangular gates. Guess what kind of gates are mostly done, you know, in irrigation ditches and LA water channel, blah, 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 stuff like that. They're rectangular most of the time, so you can use those with confidence if the gate's rectangular. Okay, so here's our picture of a submerged gate. And let's see. Yeah, okay. Okay, it looks like that picture, but the top of the gate does not touch the free surface. The top of the gate is submerged down into the water. If it helps you, I'm going to help you visualize it so you maybe it's a little bit clearer this way. Free surface, gamma water. So you can find on that, you can find FR and you can find Y sub R using equations. You can find FR, you can find YR using pressure prism. Over here, I showed you, they both give the same answer. Okay. This is your additional homework for Monday. You proved to me that you get the same answers for FR whether you use the equations, if they are, or whether you use the pressure prism, something like that. The pressure on that gate, just so you know what you're looking at, free surface, pressure starts out 0 at the free surface. This is the pressure at B. This is the pressure at C. There's a picture that goes with that surface. It's not a triangle. It's a trapezoid called a pressure prism. So do what I did over here. Try and find what the FR is by looking at these guys. Okay, how far down to what fluid? Water. How far down? Figure it out. What fluid? Water. How far down? Figure it out. What fluid? Water. You know these two pressures. You know this area, 45 degrees. You'll get the same thing. Show me. You get the same answer whether you work it with the pressure prism model or whether you work it with the equations. This gate's rectangular. It's 1 meter, 1 foot into a blackboard. Okay, so add that to your Monday homework. All right, now. Okay, our next topic out of chapter 2 And as you can see from the course syllabus, chapter 2, and there is 5 class meetings. No other chapter in the whole book has 5 class meetings devoted to it. It's big. There's a lot of topics in it. Okay. By the way, today it says we're supposed to be discussing forces on plane surfaces. Yeah, we are. We just finished it. We're going to start forces on curved surfaces, which is the topic for Monday. But we're getting ahead because we're going to have more difficult times with chapter 3 and 4. So we're going to build up some fat in the course, so that when we have those more difficult chapters, more difficult than this one, we have some extra time there to discuss homework problems and other things you might have a question about. So we're ahead of the course syllabus. That's the reason why. Okay, now, of course, this is all for plane surfaces. A lot of the surfaces in the real world aren't plane surfaces. They're curved surfaces. You've got some kind of drainage canal carrying water like this. Yeah, this is a curved surface. You can't do that with those equations I gave you. So we'll look now at curved surfaces. Okay. So let's see in the textbook what they tell us about that. Okay. He has 1/2 a page on page 68. No real derivation given. It's all words pretty much, a couple of simplistic equations. He kind of walks you through it by words. They don't go through a heavy derivation like some books do. Most books kind of just give you how to find these forces, but they don't go through all the in-depth theory. So we're going to follow the same approach that the textbook does. Here's how you find forces on curved surfaces. Okay, we have vertical and horizontal surfaces. So if you have some curved surface underwater like this, here's the curved surface AB. You can have a horizontal force on that surface and a vertical force on that surface caused by the water. If you combine them, you get a resultant force. Okay? And you can also find the angle FR. And we'll find this too. You can also find the angle theta that it makes with the horizontal. Okay? The sine or cosine of whatever you want to do. FH divided by FR or FB divided by FR. So, 2 things. You can find the magnitude of the force and the direction of the force. Okay. But the serious question is, how do you find the horizontal and vertical component? Well, here are the rules in words. So So, horizontal component. F sub H is the, what we do to find F sub H, project the curved surface onto a vertical plane. And then use the rules previously discussed. For vertical surfaces. Some textbooks go through this derivation. Other ones, like our textbook, choose not to. It takes about 2 pages, 1.5. Okay, so if we've got a curved surface, I'll just draw the picture over here. If we've got this curved surface that looks like this, curved surface AB, to find the horizontal force on that curved surface, first step is we project that curved surface onto a vertical plane. Okay. There it is right there. There it is right there. What's F sub R? You know, it's gamma H sub C times A. There's H sub C, here's gamma, and there's the projected area. Not the actual area, the projected area. Very simple. The way you find the horizontal force on a curved surface is you project the curved surface onto a vertical plane and then solve the problem the way you previously did for a vertical surface, plane surface. Gamma H sub C times A. The line of action the same way. So find Y sub R same way as previously. Y sub R equal Y sub C plus I sub XC divided by Y sub CA. Okay. Now, FV. Okay, FV, the vertical component. Gamma times the volume. This V with a bar through it means volume. The reason why the bar's through it, because when you see a V like that, it means velocity. So they don't want to confuse velocity and volume, so they put a bar through it. What volume? Okay. The volume of the fluid above the curved surface extending to the free surface real or imaginary. Okay, the equation is very simple. Gamma of the fluid times the volume of the fluid above the curved surface going all the way vertically to the free surface, whether that is real or imaginary. Okay. AB. Free surface. Go from the surface AB, vertically up from the endpoints, endpoint A. Go up until you hit the free surface. Stop. Point B, go up vertically until you hit the free surface. Stop. That's the volume. That's the volume. What is it? Oh, I don't know. It's a rectangle. There's a rectangle right there. There's this little segment right here. This dimension, if it's square, is square, it is square. R squared minus 1/4 pi r squared. That's that little piece right there. So you got to do some geometry. Yeah, so, but it's really simple. Oh yeah, you say, well, why? Well, the why is a mathematical proof, which isn't in our textbook. I went through 3 textbooks today. I finally found one. Gosh, the book was 1965 or something like that. A lot of books don't even put it in there anymore. They just plop it down like this. I wish we had the time to go through those gory details. We don't in a quarter-long course. So there are the magic rules, what we do on curved surfaces. Okay? Our textbook kind of does it a little bit differently. I don't think it's as good as this, but that's okay if you want to work it his way. But I think this way is really clear if you say it the right way. The volume of fluid above the curved surface, vertically up to the free surface, whether the free surface is real or imaginary. I'll show you a case just a little bit where the free surface is not real. Okay. So let's take a look then at...
Professor? Do you mean volume over A to B instead of velocity?
Okay. This one over here?
Oh no.
Oh, where?
The actual...
Yeah. Thanks. Yeah, I saw my little bars over there and I put my bars. Thank you so much. Yeah, I do. These guys are all fluids again. Okay. Line of action. This guy we know, A sub C. This guy, the force goes through the centroid of the area. 15 seconds here. I'll put that down. Okay, so this force acts through the centroid of the area, the vertical force. So it's going to act over here somewhere. Why not right in the middle of here? Because there's some more area on the left side. There's more area on the left side than there is on the right side. Therefore, I expect FR to be to the left of the center of this rectangular piece. See, there's 2 pieces. If you want to do it this way, you call this piece A1, and you call this piece A2. And you can find the centroid of that. Use some moments about some line. I don't know. This line right here? Sure. A1 times this distance plus A2 times this distance equal FV times that distance. Solve for the unknown distance. It's a pretty straightforward calculation. So you can find that location. Is it important? Oh yeah. If this is a gate with a hinge, is the gate going to rotate clockwise, counterclockwise, or stay in place? You have to know those distances to some moments. Okay, so now we have 4 things here with curved surfaces. First of all, we break it down into vertical and horizontal. Horizontal, project the curved surface onto a vertical plane and treat it just like you did a vertical surface in pages past in chapter 2. You can find the magnitude, F sub r, horizontal. You can find where it acts from the free surface, straight down. H sub c is the same as y sub r. Don't forget, if it's vertical, h's and y's the same thing. Second force, vertical. Define that. take gamma of the fluid times the volume. What volume? The volume from the curved surface extending vertically up to the free surface, real or imaginary. Where does that force act? It acts through the centroid of that volume V. Okay. Once you've got those two, what do? You find the result. Here it is. Once you find the result, you can find theta. Problem solved. Find the resultant force and where it acts. Okay, so that's the procedure you use for curved surfaces. All right. So let's take an example. All right, let's see. This is solid surface down here, and we have a long cylinder. So the length of the cylinder into the paper diameter of the cylinder and the length of the cylinder diameter 2 feet. The length is 1 foot. Make sure it's 1 foot. Yeah. Okay. Let's see. We have water on both sides. Water on the left is up to here. Water on the right is up to here. Okay. We're supposed to find the resultant force on the cylinder due to water. And also find the angle theta it makes with the horizontal. Make sure it's horizontal now. Okay, find that. Okay. I'm going to blow this up bigger now so we see what's going on here. I'm going to break it down into several points. 1, 2, 3, 4, starting up here. 1, 2, 3, 4. Okay, water over here. Water over here. Atmosphere above. Diameter is not right. Diameter is 4. Radius is 2. Sorry about that. Diameter is 4. 4 feet. 2 feet. Center point. Okay. You can't do it all at once, obviously. You have to do it piecemeal. So we'll take the first one. Let's take the, I guess I did horizontal on the left-hand side. F horizontal on surface 1, 2, 3. Okay, here's the rule. To find the horizontal force, project the curved surface onto a vertical plane. Okay, there it is. It's projected onto a vertical plane. There it is. On my paper. What do I see looking at it? A rectangle. What's the base? 1 foot. What's the height? 4 foot. What's FR? Resultant? Gamma H sub C A. What's gamma? Water. What's H sub C? Distance of the centroid, 2. What's the area? Here it is, 4 by 1. £500 force. Which way? Pushing to the right. Okay. Surface 3, 4. F horizontal on 3, 4. Gamma H sub C A on project surface 3, 4, as the rule says, on a horizontal plane. Okay. A vertical plane. Pardon me. There it is. How far below the free surface is the centroid? Half the way down. Half of 4, half of a, this is the radius. Half of 2 is 1. 62.4 times H sub C, 1. What's the area? The radius, 2, times into the paper, into the blackboard, 1. £125. Which way? Pushing to the left. Okay, now we'll do the vertical. I erased it, but I shouldn't have. I'll still tell you. F vertical on 1, 2. F vertical on surface 1, 2. Here's the rule. Take curved surface 1, 2. Extend that curved surface to the free surface. Okay, there it is. The volume is the volume between the curved surface and the free surface. There it is. The vertical force is the weight of the water in the blue shaded area. Gamma times the volume. Okay, the volume. Take that square. 2 feet on a side. 2 by 2 by 2 by 2. Square. Subtract off a quarter of a circle. 1/4 pi r squared. So a square. R squared, radius squared. Minus pi r squared divided by 4. R equal 2. Put the numbers in there, 53.6 pounds force. Which way does the water push on the surface? Down. F vertical on 3, 4. 3.4. Gamma times the volume. Gamma, 62.4. And by the way, there's also, you know, there's a 1 here because it's 1 into the blackboard. I'll put the 1 sometimes. Okay, here it is. Take the curved surface, 3.4. Extend the ends of that curved surface up to the free surface. Now, if I go up, there's no free surface there. Well, you saw my comment in parentheses. Real or imaginary? You pretend there's a free surface there. Is it this free surface or is it this free surface? Well, look at my finger. Which one can I go to in the same fluid? This one. Can I go under here and squeeze through there and go up there? No, it's closed down there. So I go to this free surface. There's the free surface. Is it real? No, it's imaginary. There's the volume of imaginary fluid above the curved surface extending to the free surface. What is it? Pi r squared divided by 4. Put r equal to, I won't go through all those details, put r equal to, and you get 196 pounds. Of course, the water wants to push up on it. Okay. Last one.
Professor? Sorry. That one you have to multiply also by 1, right?
Yeah, you do. I'm going to forget that one sometimes, but it's, yeah. But if this is an exam and it's 2 meters into the blackboard, put a 2 in there. Yeah, right, thanks. Vertical force, finally, on the bigger one, 2.3. Gamma times the volume. What volume? The volume of water extending vertically from the curved surface up to the free surface, real or imaginary. Point 2, go up to the free surface. It's real. Point 3, go up to the free surface. It's real. That's the area. The volume. There's your area times 1 is the volume. What is it? It's a square plus a quarter circle. Okay. So we have gamma of 62.4 times square, r squared. That's V1. This is V2. V2, quarter circle. Put r equal 2 and solve the problem. Or 46 pounds. Which way? It wants to push. This pressure down here is bigger than the pressure there, so it wants to push up, of course. Surface 2.3, so it's up.
Pi squared over 4.
Yeah. Thanks. Okay, now we add them all up. All right, the total horizontal force then equal over there, 500 to the right, 125 to the left. 375 pounds force, and that's pointing to the right. Okay, F, vertical, equal, let's call up positive, 446 plus 196, minus down 53.6, equals 558. I rounded off. And that guy is up. So I have horizontal force and vertical force is up. And I combine these to get the resultant force, F sub r, at angle theta. So the resultant force then on the whole cylinder is the square root of FH squared plus FV squared. Do the math and you get 697 pounds. The angle theta, I use the arctangent, 558 divided by 375, 57.3.5. So here's the last picture. Water up here. Water down here. Okay, here comes the force. Acting through here at an angle about 60 degrees almost. There. Angle theta. That resultant force has to go through the center of the cylinder. It has to go through the center of the cylinder. Why? Because the pressure force at every point on that cylinder, the pressure force at every point on that cylinder from the water also goes through the center. Here are the different pressure forces going through the center. Where's the biggest pressure force? Oh, he's right down here. He's real big. And they get smaller, and they get smaller, and they get smaller, and smaller, and smaller. This is how the pressure forces look. The biggest pressure is where? Way down here, way deep down here. Where's the smallest pressure force? 0 right there. 0, bigger, bigger, bigger. And where do all these arrows go? Don't forget, pressure X normal to the surface. All these individual little pressures go through the centroid. So guess where the resultant force goes through? The centroid. So it makes sense that way. Okay, big long problem, but boy does it tell a lot of stories. It tells a lot of stories. Surfaces above, surfaces below, fictitious free surfaces, real free surfaces. This is an example that goes through all the possibilities in curved surfaces. We won't get into anything more exotic than quarter circles, semicircles, or full circles. We won't have any integrations, but if you got some strange shaped curved surfaces, you'd have to integrate. Really, really messy, really messy. We won't have time for that. Okay, good stopping point, so we'll see you next week.